Thank you, Debo, for the introduction. Before I start my talk, I want to poll the audience. Are you guys familiar with Byzantine fault tolerance? Okay, because I will not be describing Byzantine faults, but I'll be focusing on the other parts, that's reconfiguration friendliness and the randomness part. So just maybe if you're not familiar, Byzantine fault tolerance is to tolerate faults that can be arbitrary. So they are not bound by any form of attacks. They can do any attack that they want, so they can deviate arbitrarily from the protocol. So we are going to be concerned with the randomness generation under such faults. Okay, so I'm Adithya Bhat, and I'm from Purdue University, and I'll be talking about how to generate randomness in the distributed setting, tolerating Byzantine faults, under the constraint that you want the system to be reconfiguration friendly, i.e. you want nodes to leave and join the system, and ideally you want efficiency. Okay, so let's dive right in on the history of some randomness. So there's a protocol called coin toss protocols. So these are historically used to generate one random number. So it's a dedicated protocol that a bunch of parties run, and they'll generate one random number. So it's used one time. Whereas a random beacon protocol keeps on generating a sequence of random numbers. Its whole job is to it's like produce a sequence, and it's multi-shot or iterative. So it keeps there's a mapping from every round to a random number. It doesn't stop. So it's not one shot. Some of the applications of randomness is that you can use it to, for example, you and your roommate are fighting who will do the dishes today. You decide that you will have a system, and who's going to start, right? You can use a coin toss protocol because it's a one-time thing. Once you start, you'll never need a coin toss again. It's also used in zero-knowledge protocols. So let's say you just want to terminate, you need one-time randomness, you can use a coin toss protocol. And also in two-party MPC. Whereas a random beacon protocol is a continuous service, right? It keeps on generating beacons. So where would you need a random beacon? So in lotteries and casinos, right, they'll keep on needing randomness because the slot machines will keep working. So you will need a continuous sequence. Proof of stake systems will also they run forever technically, and they will also need frequently they'll be needing randomness. So it would make sense to have a random beacon protocol providing inputs to proof of stake systems. Asynchronous agreement in the asynchronous world, due to some impossibilities, randomization is mandatory. So you will also need a randomness beacon protocol there. There's MPC, and if you need a coin toss, you can always pick one of the randomness numbers from the beacon itself. So a randomness beacon serves as a coin toss as a service. So let's see some real world examples. So this is a financial cryptography 2022 submission page. So the way they did it is on September 3, they'll fix a block height of Bitcoin, and they'll see the last, so that block height was 698980, and this was in the future. So once that block was mined, they looked at the hash of that block, and based on the last hex digit of that hash, they determined what the deadline is going to be for the conference submission. Because most of the time, people would abandon the submission on the last day because maybe they just had one section coming in late or so on. So to make the system fair, they said, let's have a random additional days. We'll give people additional days, but it should be random. And they used the Bitcoin block as the source of randomness. Now the question is this a coin toss protocol or is this a random beacon protocol? What do we need and what did they use? This is like a quiz. So you guys need to think about this. So what they press the wrong button. So what they ended up doing is since they used the Bitcoin hash, so they basically used the beacon protocol, right? Bitcoin didn't generate that block just for this conference. So they keep on generating. So they can be treated as a random beacon, and they use one particular block for their purposes. So this is using a random beacon protocol as a coin toss. So it has its applications. In the real world, so these are some real world random beacon protocols. You can even go now to drand.love, that's the website, and you will find a random number. They keep generating a random number every 30 seconds. And there are proposals to generate random numbers from solar cells because there is some photovoltaic, the amount of energy generated from The cells itself is random between 3.3 to 3.7, and they say let's extract randomness from this. A cool thing that Cloudflare is doing is they are using lava lamps for their randomness. So people are looking for randomness in all sorts of weird cases. Of course, right? These are not publicly verifiable. If Cloudflare says your random number is 0, 0, you have no way to verify because the lava lamp would have changed its state by then. So by the time you go to their office, it's too late. They also make some strong synchrony assumptions, timing assumptions. They're not distributed. The lava lamps are in the Cloudflare's office. The solar cells, of course, are in somebody's farm, right? You can't use it. And again, they're not publicly verifiable. So we have problems with these ways of doing it. So with this in mind, let's look at some notations and definitions that I'll be using in my further discussions. So I'll just cover up the definitions. So first, we know randomness beacon needs to be random, right? For that, we need to talk about unpredictability. So we'll say that a beacon protocol is in some round. It means that there is at least one honest node is in that round, and we are usually looking at the lowest round. So especially since we want to make weak timing assumptions, let all the servers in the system be at different rounds. So say 1, 2, 3, 4 up to 10. Then we'll call the protocol to be in round 1 because the slowest honest node is in round 1. So then we'll say the system is in round 1. And now from this round, we'll define what D absolute unpredictability is. So we'll say a protocol is D absolute unpredictable if the adversary can, if the system is in round R, and if the adversary can predict up to R plus D and no more. So R plus D plus 1 onwards, if the adversary cannot predict, then the system is R plus D unpredictable. Right? So if in the previous example, if servers were in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the system is in round 1, and if the adversary can predict all the way up to 10, then the unpredictability is R plus 9, right? So it's 9 absolute unpredictable. So this is what we mean. And of course, the best unpredictability is always 1, because if the system is in round R, a rushing adversary will always see whatever you use to compute the R plus 1 beacon first, right? So the system, if it's in round R, will it's always possible to see 1 round into the future. So 1 is like a lower bound. You can't go below 1, according to this definition. Also, this definition only holds in synchronous systems. So when you leave, as you said, in asynchronous systems, it is always possible that some slow honest servers are in lower rounds. So this definition kind of becomes infinity in that case. So we'll have to patch the definition. But note that this is only for synchronous systems. OK, so now let's go deeper into defining what randomness is. Okay, so randomness contains 2 properties. The first one is unpredictability. So intuitively, it means that with no information about future rounds, I should not be able to tell what this value is going to be. This is what an intuition is. And we want to also say that an adversary cannot bias the distribution of whatever the output is going to be in the future rounds. So we want to prevent bias resistance. So some classic examples of unpredictability is, for example, if an adversary can directly tell, okay, the next bit of the random number that the protocol will output for the next round will have the last bit 0. So this violates unpredictability because he can clearly predict. And if this works with a very good probability, then yeah, you have broken unpredictability. And bias resistance, an example would be if you can see the random number and decide, okay, let me kill the system for this round. So let me decide, okay, if it's odd, I'm not going to make the output happen. So I can skew the distribution to make sure that there are less odds than previously before. So you don't want to let the adversary bias the distribution in such ways. It turns out an elegant definition for this is to say that let's take all the outputs of the random beacon and make it a long string. And we argue that this string should be uniform. So this is a very clean way to capture both of this. So turns out if it was biasable, then the string wouldn't be uniform because some places there will be more odd, and an adversary can distinguish this bit from a random string. And at the same time, if it was unpredictable, he can look at part of the string and predict the next part. So then again, he could distinguish. So this one game kind of captures both unpredictability and bias resistance, and this is what we'll use in our in our security definitions, but I'll not describe this. But just for your information, this is the modern definition of randomness for randomness beacons. And coming to the meat, so state machine replication is a distributed protocol between end servers and clients, and it informally satisfies two properties: safety and liveness. So a state machine replication, just like a random beacon protocol, generates outputs a bunch of blocks or a bunch of transactions in some order. And safety says that these orders are always the same for two correct people. If one honest node sees first tx1 and tx2 in that order, then all other honest nodes will only see tx1 and tx2 in that order. They'll not see tx2 maybe in a different order. This is what safety means. And liveness means that if a client has a transaction, it will eventually be processed by the servers, and it will appear in this log. So informally, this was defined this way to say that your state machine replication protocol cannot get stuck. This comes historically from that reason, because there used to be protocols that can get stuck under the network conditions. So they wanted to somehow rule that out, so that they wanted to put that in the definition. So they said, yeah, let's define it this way. This way, if a protocol gets stuck, eventually this property will not be satisfied. And instead of painfully saying order of transactions, we'll just deal with blocks. We'll just say that there is a hash chain of blocks, and from this you derive the order of transactions, and you will just deal with it. So our SMR protocol will just output a hash chain of blocks. So some of the cryptographic assumptions that we do is some standard assumptions like PKI, digital signatures, random oracles, and the QSDH assumption. So the QSDH assumption is given g power alpha square up to g power alpha per q. You cannot compute for any c g to the power 1 by x plus c. So this is a simple assumption, and the setup involves q plus 1 elements. And it's also called as a structured reference string setup. So as this is, we are not going to assume bulletin boards. We'll have to open that bulletin board abstraction and implement things. And as you implement a protocol, you will have to define what the network assumptions are. What happens when you send messages? Because this is very important to determine how many faults you can tolerate. So we'll assume a bounded synchrony. So this is different from the synchrony assumptions that is standard in the literature so far, because this history dates all the way back to 1970s till 2023. And most of them have used the word synchrony in a very incorrect fashion. So I am clarifying what assumption we are using. So we are using delta bounded synchrony. It means that the only assumption we make is if any honest node sends a message at time t, it will reach the other recipient, if it's correct, by time t plus delta. And this delta everybody knows. So basically, the whole system makes an assumption that any messages sent will be delivered by delta. So that means if I don't receive a response within 2 delta, clearly the other person must have received it and they didn't respond. So I know that they didn't send me a message. So we can use this fact and make a lot of improve the fault tolerance. But this is the only assumption we make. Because classically in existing protocols, there's another system that they use is they call lockstep. So they, at least in literature, you will find protocols where everybody is in one round. They'll send the messages. They'll all move to the next round. And magically, by the next round, they have received all the messages. All honest nodes have received all messages from the previous round. This is a very strong assumption. We are not under that model. Our only assumption is there is a value delta. Everybody knows it. And messages will be delivered within delta. And this is what we call as non-lockstep, because we're not forcing that all people are in the same round. All people will move together to the next round. We're not making such assumptions. Okay, now let's define what the adversary is. Obviously, is going to be computational. And up to t, we'll define t as the number of Byzantine faults. And we'll define f as the number of real faults. We don't know how many these are. So these are the number of people actually misbehaving. So even though the adversary has corrupted t, maybe most of them are behaving according to the protocol. Maybe he's just trying to do something, orchestrate some complicated attack where everybody is behaving correctly, but one person is doing something. So in that case, f will be 1, but despite t being up to how much ever we allow. And the corruption can be static or adaptive depending on the protocol. So we'll be describing 3 protocols, and I'll tell which one we are going to assume for which protocol. And obviously, we assume that the adversary is rushing, so he can see all the messages before it's delivered. So I told you there's a T and T plus delta, right? So the moment you send, the adversary sees it. So we just assume this. So what are the challenges in why is this non-trivial and why is it a hard problem, right? So let's explore some challenges. So we said that our randomness beacon should output random numbers, and this random number should be unpredictable. Which means that we have to take into account for every round, whatever you are going to output, that number should be a function of T, more than T inputs. And it should come from more than T servers, right? Because if it's coming from less than T, the adversary can clearly predict because he knows whose output you're going to use. So we need to somehow, unpredictability means you need more than T inputs. Bias resistance means that to prevent an adversary from seeing, so let's say from seeing the random, because he's rushing, he can see the random number. And once he sees, if he can prevent that from ever being reconstructed or ever being actually brought out into the system, we need to ensure that you use some form of commit reveal protocol. And with the additional constraint that if you commit, reveal is guaranteed. Because you don't want the system to commit and the adversary sees it and decides, let's not reveal this one. So that biases the distribution, despite being unpredictable. So we don't want this to happen. So which means that if you commit, you should guarantee reveal, which clearly says that the number of faults, you need to use some form of secret sharing. Also, you could use VDFs and other forms, but the general gist is this way. You have to guarantee reveal. Since we want optimal communication complexity, we have a budget. So you cannot cross the order n square communication complexity. So we have a budget of this. We cannot do arbitrary protocols. And because we want reconfiguration friendliness, we cannot assume threshold setups. You cannot secret share beforehand and use that later down the protocol. So therefore, you cannot have threshold setups. Without threshold setups, you don't have constant size quorum certificates because most of the existing state machine replication protocols take advantage of this to bring down the communication complexity. So we don't have this power. So that's what we mean by reconfiguration friendliness. And because we are in delta synchrony, the optimal fault tolerance is actually up to half. So we know that it's possible to tolerate up to half. So, and in our random beacon protocols, we don't want to be away from optimal. We want ideally a random beacon protocol to tolerate how much ever the system can allow. And that turns out to be half. So we want a random beacon protocol to also tolerate up to half Byzantine faults. So let's look at the landscape of random beacons. They all have some drawbacks. We are not happy with the current landscape. They have an X everywhere. So, and they are not reconfiguration friendly or their unpredictability is bad. So in our work, we come up with these 3 protocols at the bottom. And the best so far is the last one, which is our most recent work. And it has all as a classic research paper table, we have tick marks and the best numbers in all the columns of our table. So very happy for that. The catch was until now it was not adaptively secure. As of May 2023, which is right this month, it turns out that even that's solved. So it's not solved by us, but somebody else solved it for us. So right now this is a very good thing. Okay, so let's go. I will not go into this protocol, but let me give you an idea of what the state machine replication, as a black box, what are its properties. So we come up with our own state machine replication protocol. And this is what it looks like if you try to read the paper. We add some cryptography to it. And finally, we get our beacon, right? So this is how we construct our randomness beacon. But this is the landscape of state machine replication protocols. So there are so many properties that they have, and you need to pick your flavor here. So if you are lactose intolerant, you lose some properties. You have to pick some other things. And if you are vegan, then you'll have more. You'll have to cut more options. Basically, that's how you choose. So let's say you want high throughput, you want lower block period, and you pick your SMR based on the properties that it has. So this is how you would find a protocol of your choice. But now we are in the context of randomness beacons, right? So we need to pick our SMR protocol. What properties do we care and what properties do we don't care about? So let's ask that question and let's look at the landscape. Turns out we care about communication complexity, but none of the others. The other properties we don't care. How many signatures you do, we don't care. What's the throughput, we don't care. Does the latency matter of SMR, we don't care. So it turns out the only thing we care about is communication complexity, but we also can't use threshold setup, right? We want reconfiguration friendliness. If you make a threshold setup, if one person leaves and the other person joins, you have to redo that setup. That is O of n cube and it breaks the communication complexity optimality. So we cannot use it. So we need some other way to do it. So that leaves us with basically no existing work that we can use for our system. So we had to go back to the drawing board and implement our own. So we did that, okay? So we looked at existing SMR protocols. We added some erasure codes so that it can tolerate larger inputs. And once we do that, we construct an SMR with some nice properties. The properties are that in every round, you'll have a leader. And this leader can input order n size string to the system. So he can propose something. For example, he can propose his list of favorite n people, right? All the people in the system. Or he can propose some secret sharing, or he can give everybody some nice values, right? So you have order n space that you can input. Every person, in their turn as a leader, can input order n size strings. And the property that we guarantee is that if that leader was honest, he's following the protocol as is, then every server is going to commit in that round. In that right round, at the end of that round, everybody will commit it, okay? If the leader is honest. So, but let's look at the other way around, right? We don't know if the leader is honest. As a party in this protocol, you have no idea who's honest, who's dishonest. But what you know is whether if you committed that block. So you will know whether you accepted that block. Once you accept that block, you don't know if others have accepted as well. So you have output that block, and you have no clue if others have output that block. So, but what we do is our SMR protocol guarantees that if you output a block, all future chains or all future leaders' proposals must extend this block. So our black box SMR guarantees this. So as I said, we have a hash chain of blocks. So when the next leader proposes, he has to link back to the previous round if he was honest. And because of this, if I output a block, I know that all future chains must somehow extend this committed block. This I know, but I don't know if others have committed yet, right? This is the key problem, and turns out that if you use round robin, for example, round robin protocols, and you know that there are only T Byzantine faults in the system, if you just wait for T plus 1 rounds, you know somewhere in there's going to be an honest server, honest leader. You don't know which, but it doesn't matter. If you commit a block in this round, at the end of T plus 1 rounds, you now know everybody must have committed this block. Why? Because somewhere in between, there is an honest node. And because I committed, all future chains must extend this. Therefore, by the end of T plus 1, somewhere they have committed. Everybody has committed. So we can now take action after T plus 1 rounds on whatever we have output. So there's a lag now of T plus 1. Once you propose, by the end of T plus 1, you know something nice will happen. So we need, the key requirement here is that, of course, we agree on who the leader is. So if you are using some magic leader mechanism, we need to ensure that I and you pick the same leader. We don't want both of us picking different leaders. Then there's a problem again. So we need to agree on who the leader is. So to be careful there. So yeah, this is just the argument that I just said. So if the leader of round R is honest, everybody's going to commit in that round. But in the next sequence of, if in the last T plus 1, someone was honest, and they'll have the same view, and they'll basically in T plus 1 rounds, you will all commit. So that's the guarantee that we get. So finally, recapping all the features of our SMR. Again, leader can input order n size strings. And the communication complexity is always order n square per round. So this is a key important part. So we have our optimal SMR now. But the latency is actually T plus 1 round. So when the leader inputs, for that round, the commit is actually after T plus 1 rounds. Also, in our most recent work, we have something called as the optimistic responsiveness, which means that if 3/4 of the system is behaving correctly, so if F, the real faults, are less than 1/4, you can actually get commit speeds independent of that delta that I told you. So you can commit at network speed. The problem with committing at delta is, say, delta is 1 hour, right? Now your commit is actually maybe some function of this delta, maybe 3 hours, right? Now what if the network speed is in milliseconds? So ideally you want maybe 3 round trips, 4 round trips, and ideally 4 milliseconds. Commit in 4 milliseconds, right? Even though your capital delta is hours. So that property you can get if F is less than 1/4. We can add this to the existing SMR. Now let's finally dive into randomness beacons. We have solved one part of the problem. We have our nice black box SMR that gives us some nice properties. It's black box only for this talk. In the paper, it's white box because we described how to construct such an SMR in great detail, painfully, taking a lot of pain. But okay, let's discuss some randomness beacons. So the general idea is as follows, right? You have all the servers, right? They will come up with some randomness numbers. We don't know where they may be using lava lamps themselves. We don't care. They come up with some random numbers. We kind of lock it. This locking is a secret sharing scheme. So they lock it using some publicly verifiable secret sharing or some other verifiable secret sharing scheme. So they'll kind of lock it, and they'll input into the SMR in their turn. So they will take turns. Each one becomes a leader, and they'll input into the SMR. The SMR will take some T+1 rounds, right? And finally, at the end of T+1 rounds, everybody knows either that this secret sharing worked, right? Because we committed something from that round, or they know nothing, we didn't commit anything. We kind of somehow skipped that round, right? Nothing from that person was committed. So we know these properties at the end of T+1 rounds. Maybe the chain is shorter than we expected at the end of T+1 rounds, then we know something wrong has happened in this round 1, right? Then what we'll do is we'll make sure in the next time he's not eligible to be a leader, this person, whoever blocks we didn't commit, okay? And finally, sometime in the future, whatever was secret shared, the random number, we are going to use it to construct our beacon. We'll input into the magic function, and it's going to output a beacon. I will describe these magic functions, but this is the general overview of how our beacons will be constructed. So let's look at construction 1. So this is called G-Randpiper. So Randpiper is our SMR protocol, the first SMR protocol, and G is good Randpiper. So it's a good scheme. So it's a starting scheme. It's training wheels, randomness beacon training wheels. So the properties of G-Randpiper is that it has always quadratic communication complexity for per beacon. We'll never cross this, which is what we wanted, right? We want good communication complexity. The unpredictability is minimum of kappa and T. And you will see, hopefully you will see it as I describe the protocol, why this holds. The argument is for small n, maybe for n equal to 7 or 11, the T will be half of it, right? So for 11, it will be 5. Within 5 rounds, an adversary can only predict up to 5 rounds into the future. But if your n is like a million, then you pick a security parameter, kappa, say 100, then the adversary can only predict up to 100 rounds into the future. Because it's highly unlikely that so many rounds, the reason for this is that you have to corrupt the leaders into the future, and that's how you know the beacon. Highly unlikely that all the next 100 are all Byzantine. So that's how you get it. And the magic trick we use, the cryptographic trick to hide the secrets, randomness numbers, is PVSS. So we use PVSS schemes. And we make sure that the leaders are chosen using the randomness beacon itself. So the beacon will output some randomness. We use that randomness again to choose our leaders randomly. So we are going to reuse our own randomness. Let's see the construction visually, right? This should help us cement the protocol. So you have a round robin, n equal to 5 here, and up to t less than n by 2. So up to 2 servers could be Byzantine. So, and in this case, we'll be using round robin. Let's try to simplify our life now, because let's add one layer at a time. That should help us easily understand. And in this case, we are using round robin. So 1, 2, 3, 4, 5, and again 1 will repeat. So in round 1, So server 1 will pick a random number, maybe using its own lava lamps or solar cells, and does PVSS encryption on it. So the property of PVSS encryption is that if I give you this string is order n long. Right? Remember I told you SMR can only take in order n sized inputs, right? Strings of order n size. So the PVSS string is order n sized, and the nice property is if I give you this string, using some local computation, you can ensure that everybody has correct shares. So this is this is publicly verifiable secret sharing. So anybody can verify that everybody's shares are correct, using some magic, using some cryptography. I'll be happy to explain this to you later, but this is the black box as of right now. And every server is going to input into the SMR, right? So in this example, server 1 will take this S1 and feed it to the SMR. Next round, server 2 will take his own random number. Because it's a hash chain, right? He's going to refer to the previous block, and he's going to input that into the SMR. And everybody is going to do this, right? So they're all going to pick a random number, feed it into the SMR. Now, but at the end of t plus 1 rounds, as I said, and t is 2 here. So at the end of 3 rounds, we know either S1 got committed or some representation of S1, right? Because nobody knows S1. But we know that whatever he proposed, is it committed? Or we know nothing was committed. We know that either he failed to input something into the system, or we know something got committed, right? And this will happen like a pipeline. So in the next round, you know whether 2 has committed something or whether he has proposed something. So basically, you know. And what we'll do is, we are going to look at whether something was committed and then only allow him to become leader again, so next time. So if he was bought, if he did not commit anything, he's not allowed to be leader. So in 6th round, 2 will come as a leader because 2 committed something. So we are basically disallowing people from being leaders. So the box assumes everybody has the right shares. So it's a big string. Your share will be inside one piece of that. But so using some crypto, I can check that everybody else's shares are correct, and I can decrypt my own piece in that. PVSS is just a cryptographic way to generate an order n size string. And it consists of 2 components, encryptions and some additional things called commitments. No, the leader secret shares S1 for round 1. So in round 2, he'll pick an S2 and secret share that. So each person can verify that everybody's shares are correct. At the same time, there's another component in that PVSS called an encryption. They can decrypt it to get their share that they'll use to reconstruct later. No, in PVSS you can. You can guarantee that everybody's shares are correct. It's the beauty of how it's constructed. I can guarantee that this is indeed a t plus 1 size polynomial and everybody's encryptions are correct. You cannot see the encryption, but you can guarantee that they're all correct. No, it turns out there's a beautiful way to do it. Yeah, so the high-level idea is you take a polynomial of degree t. So that means the t plus 1 points are needed to reconstruct that polynomial. So you take 2 generators g and h, and to the g, g to the power p of 1, g to the power p of 2, g to the power p of 3. This is called the commitment vector. So you put g to the power pi. It's n elements you put. This is called the commitments. And then what you do is servers also have a PKI, right? So they'll have their own public key of the form h to the power some secret key. So there are n public keys with their own secret keys. And you raise this public key to the p of I. And using discrete log equality proofs, which are constant size, I can prove that each commitment maps to the correct encryption. So basically, g to the power p of 1 and pk1 to the power p of 1 have the same exponent. So I can prove this using NIZIC proof. And and I can check whether these g to the power p of 1 through p of n are in a degree t polynomial using a erasure coding check. So there is a check there, where you take a random vector, and if you multiply, because it's going to be orthogonal to this nt sharing, it's going to be dot product is going to be 0 in the exponent, so you'll get 1. Because of this, I can check that it is an NT polynomial. And because every discrete log equality holds, it must be the case that everybody has the correct sharing. So I can just decrypt mine. So this is how, on a high level, this PVSS works. This is the magic that that basically no interaction is required to check whether everybody is happy. You just look at the string. If all the math checks pass, you know that everybody's shares are correct. So no, that our SMR will handle. So the SMR will be like, if he equivocates, then maybe there are many things that, many cases that can happen. But if something does get committed, then everybody will commit. But if something he gets prevented, then everybody will not commit. So this our SMR black box will take care. Okay, good questions. So yes, we'll prevent, if nothing is committed, we'll prevent them from being leaders. So we know by the time somebody is leader, we know last time they committed something. This we know. But we don't know what will happen this time, but we know something was committed last time. So if you are a leader, something was committed last time. So now let's look at the last committed secret, right? So now we'll look at the same sequence, but this time we'll focus on what they committed the last time. So in this case, in some round, S1 is something that they committed last time, right? The previous time, whatever they proposed. Again, if they are not, this time they don't propose, we don't care. So we are looking one step back now, and rounds backwards, right? So now we'll reconstruct this. Let's open this value, right? Because it's a secret sharing, everybody has a secret shares. They'll send this and reconstruct this S1. Not good, right? Like everybody is going to do open all the values for every round. But how do we still haven't described how do we construct the random beacon? So the random beacon will start from the first t plus 1th value, because as I said, unpredictability means you need more than t inputs, right? So from 3 onwards, our first beacon will define as follows. O1 is the hash of S1, S2, S3. We know one of them is coming from an honest node, so it will not be something trivial. So it will be something nice. And similarly, from the next round, we'll start chaining things. So the round 2 beacon is going to be S4, what we opened for this round with the previous beacon. What we opened from this round and the previous beacon. That's how we do our randomness beacons. Now note that, let's say this 4 is honest, right? Is honest means the adversary does not control it. He doesn't know S4. So he cannot do anything. Even if he knows S5, he cannot compute the beacon. So if there is one honest node in the future, he blocks you from seeing the entire chain afterwards. So all you need to do is to reduce this number of, increase the probability that an honest server is there to block this view that an adversary has. On the other side of the spectrum, if I know the next 3 leaders, I know the next 3 beacons. So this is how you get the minimum of kappa t unpredictability. If you know the next t, if you are adaptive adversary and you see that this is the sequence, I can go after them and corrupt them, learn what they committed, and I can know the entire sequence of randomness beacons. But again, no more than t, right? Because t plus 1th guy is honest. And because that t plus 1th person is honest, from that point onwards, you cannot see the beacon. So it's limited to only t. So this is why it's good and not the best Randpiper. So it's just good Randpiper. But that's basically how we construct the beacon for this protocol. Oh, I'm sorry, I'm pressing the wrong direction. Okay, so this is G-Randpiper in summary. So we reduce the predictability advantage of, so we, as described, it was round robin. So it's clearly you can predict up to t plus 1 rounds into the future. If you use the beacon itself, the randomness in the beacon to pick your leader, then you can make the whole thing probabilistic. But again, adaptive adversary, we have 0 game, right? Because he can just look at one beacon and see who the next person is going to be, corrupt all of them. So we have no power against adaptive adversary. Okay, so let's look at the B-Randpiper. So B-Randpiper stands for better randomness beacon. So it's better Randpiper. Better because not the best, because it's somewhat better than G-Randpiper, but it's not the ideal. I'll tell you why. So let's say we want one unpredictable randomness beacon, right? We had a problem with the previous one. We want immediate unpredictability, like no more than 1 round into the future. If you want such a randomness beacons, every round you should take inputs from everybody, right? And because we are looking at a secret sharing way, you have to have some order n number of secret sharings, and you want to somehow homomorphically combine all of them and reconstruct that to a big random number R1 and open that. right? We can just define randomness beacon for round R to be this hash of this combined random number. This would be very ideal if you could do it. Maybe for round 2, we'll take one more fresh sample of VSS from everybody, some secret sharing from everybody, and we'll combine all of them, and we'll make every random beacon to be inputs from everybody. This would have been so nice. But if we are feeding, but how we implement this is we are going to input in rows. So each person, because our leader is, everybody's not the leader, right? So if you wait for everybody to be a leader, input one shares is going to take a long time. So what we're going to do is every leader proposes n secret sharings, and it's going to feed it into the SMR, okay? So 2 will feed n secret shares into the SMR. Everybody's going to feed n secret shares. This will give us a nice matrix, right? From this matrix, you can consume in columns now and output your beacons, right? So that's what we do in this scheme. Now the question is, what is that lock scheme? What is the secret sharing scheme? So the fundamental question, cryptographic question that we ask is, how do you share so many secrets from different servers without always incurring O of n cube communication complexity? Because PVSS shares, as I described in GRAND paper, each secret share was order n sized long. Now, if we are feeding in n rows every round, your input is going to be n square, because n into n. And because your input is n square, the SMR's communication complexity will blow up. So we cannot do it this way. We need to think of something else. So we don't know how to do it with the current PVSS or SMR constructions. What I mean is that with the current known PVSS technologies, you cannot reduce the n secret sharing size from order n square. At the same time, we don't know any SMR protocol that takes inputs order n square every round, but somehow outputs consistency and all the nice properties. We don't know within order n square communication complexity. So if the input itself is order n square, it usually blows up by order n. So SMR adds an order n complexity. So we don't know how to do it as is, right? So what solution we come up with? Maybe we can have a compromise. So our compromise is we do IVSS. Again, IVSS stands for improved VSS. So we take a look at the state-of-the-art VSS. We add some improvements to it, and we get a communication complexity of Fn square. Now, it's a compromise, but F here is the number of real faults. So we hope that the number of actual people misbehaving is usually small, and we don't need to pay the cost defensively. So if the system tolerates half, doesn't mean the complexity is always n cube. It may be actual function of the actual faults, how many people are actually misbehaving. And we can do this using just by sharing order n. We can now input n secret shares into the system. Okay, so let's understand what is this IVSS, right? To understand that, we need to understand what the old VSS scheme was doing. You can immediately see what the problem was, and hopefully you can see why the trick that we use, how that helps. So there is something called as a bulletin board, and there is somebody called as a dedicated person called the dealer, leader, any word you can use. This is the bulletin board. And usually, to do n secret sharings, in particular to do n verifiable secret sharings, not publicly verifiable. Here, if I look at the string, I have no idea whether other shares are correct. So they're going to commit to some numbers, R11, R12, because 1 is the leader and 1 is like the index, right? We have to share n secrets. So 1 is the first in that n. R12 is the second in that n, proposed by leader 1, and so on. Oops, I'm pressing the wrong buttons. Yeah, so but the shares for this commitment, they're going to send privately. So not on the bulletin board, but separately on a separate channel, this individual shares will be given. And what we are going to post on the bulletin board is, if node 2 does not receive any share, it's going to post a complaint like, hey, I never got anything from the dealer, something fishy is going on. So they're going to post their complaint. So what the dealer is going to do, if you complain, I'm going to give your share in public. So I'm just going to post your share. Now everybody can check, right? Everybody can check whether that share is correct against that commitment, and all the complaints are resolved, and people are happy. So if the dealer was Byzantine, he already knows what's being shared, right? So posting shares does not reveal anything secret, right? Dealer already knows what is sharing. So adding the shares does not reveal any secrecy. And let's say the dealer is honest. Then Byzantine guy is complaining, does not reveal anything new to the Byzantine adversary, because he already knew his shares. Making them public does not reveal anything. So this is ensure secrecy, because adversary does not learn anything new in this scheme. Now, note that each agreement on the bulletin board translates to T+1 rounds in our SMR, because you need to know everybody knows. So here, every post everybody knows, and this has to be done in this order, right? So you have to wait for all complaints to be on the bulletin board before you go to the step where you post the shares. You cannot, because if there are more than T complaints, you know that the server is dishonest, because one honest server has complained. So you need to somehow, there is this ordering that has to happen. I.e., what if 2 is indeed honest and his complaint never appeared on bulletin board? This is very dangerous, because then reconstruction cannot be guaranteed for up to half faults. So you need to ensure that all complaints from honest servers are there in the system. Now, to ensure, in our SMR at least, everybody takes turns, so it will means that you have to wait a long number of iterations until, for one n secret sharings to finish, you have to wait a long turn. This is not good. So what we do is, this communication complexity is now order of Fn on the broadcast channel, and it's a very bad thing to implement naively, as is, in our SMR, or in any SMR actually, it's very bad. So turns out we can improve this, and that's where we observe that what doesn't need to go on the bulletin board. So what we do, same setting as before. You have a dealer and everything. You again do put the commitments on the bulletin board. You send the shares privately. What trick we use is that blames or these complaints are not on the bulletin board. You send the complaints also privately, right? And for every complaint that you receive, you're going to forward this complaint to the dealer. Hey, I got these 3 complaints from these 3 people. Can you tell me the solution? Like, can you tell me the shares for this? Now, again, the same properties as before holds. What we are going to do is, if I, as a honest server, I received 3 complaints, I forwarded them to the dealer, he gave me the shares, and I'll give it back to the 3 people who complained. And this, I'm happy now, because all the complaints I received, the server did resolve to me, right? I'm happy. I'm going to send a vote. Like, I'm going to send a message, signed message saying I'm happy for this server. Now you collect, dealer has to collect all these happy messages and put one certificate on the bulletin board saying enough people are happy. And the guarantee is that if such a certificate exists, again, secrecy will not be violated if the dealer was honest, and we guarantee that reconstruction is possible. So this is the guarantee. And notice that we reduce the number of rounds. Now all you need is one certificate, some local protocol, and one posting of all these commitments. And the nice thing is, this certificate, this voting, I am happy message, can be integrated directly into the SMR, because SMR itself has some I am happy messages regarding the proposals. So you can make the same happy message to treat as SMR happy and protocol happy. So basically 0 cost, additional cost for these messages. So it is we get a nice complexity that it becomes, on the bulletin board is O of n, but because these complaints can be, number of Byzantine parties can complain, right? So that adds another F complexity in the real version of the protocol. So finally, after using all these magic tricks, we get one absolute unpredictable randomness beacon. Now the adaptive adversary also has only like 2 delta amount of time he can predict. So if somebody learns the secret in time t, adversary, others will learn within 2 delta. So the gap is very small. Not just 1 round, within 1 round, only 2 delta advantage he has. So if it's actually in a casino, if the delta is 1 hour, 2 hours advantage is all he has. An adaptive adversary has to learn. Means in 2 hours, everybody else will also learn. And the best case communication complexity is order n square, and it's order fn square, where f is order 1, so you will get order n square. But if actually in the worst case, if all of them start misbehaving, only thing they can do is increase communication complexity, nothing else. So the worst case will be order n cube, but the hope is we will never need to hit such a situation. Finally, good, we are on time, because this is very easy to understand now that you have the background of B Randpiper and G Randpiper. This should have been best Randpiper, but this is a separate paper, so we call it OptRand, because there are some more other cool tricks we add to this beacon. So now again we were dissatisfied. We wanted one unpredictable random beacon with always n square communication conflict. We didn't want this F business. So we're kind of unhappy with the F, right? We're reading more papers, more PVSS schemes, maybe something possible. No, unfortunately, with the existing secret sharing schemes, it was we were kind of stuck. So we needed something else, right? So turns out we had to modify an existing PVSS scheme. Using that modification, we add something called as decomposition proofs. By adding this, turns out you can combine PVSS homomorphically, but still argue that there are T+1 inputs inside this PVSS by just adding an order n size string on top of a PVSS. So you can convert a publicly verifiable secret sharing into a publicly verifiable random sharing. What is this string arguing is that, again, it's a secret sharing, that everybody has correct shares. Also, it argues that this final combined string has inputs from T+1 people. It also argues this. Once you argue this, it's clear, right? Like, you know there's a random number inside this string, and all you need to do is reconstruct. So you are good to go. The question is how to do this securely. On top of that, our construction gave us another feature that we were not expecting. So this construction allowed us, so once you open this construction, you will get a constant sized message, which is the actual secret inside. And if I just give you the secret and the original string, which you have already committed, you can guarantee that this is indeed the right opening. This was not possible before, because if I give you the opening, I'll have to give you everybody's shares, so that you can also confirm that, yeah, indeed reconstructing this opens to the correct value. Turns out in our construction, just by giving the final reconstructed value, you can confirm, yeah, it is the correct opening of this PVRS. And this, because it's constant size, and because I didn't have to give everybody's shares to a person, turns out you can now, everybody can jump rounds very quickly just by sharing this opened value. So basically this opened value indicated to everybody this round is over. Let's move on. Otherwise, you had to wait until all, or you have to send everybody all the shares, which will blow up the communication complexity. So it turns out this one small trick opened many doors to us. That's why 2 achievements we unlocked at the same time. That's why we call it OptRand, because it's optimistically responsive randomness beacon. So also an independent interest, we were able to construct a threshold signature free rotating leader SMR protocol. This was not there in the literature before. We got this because of the randomness beacon. In this protocol, you cannot separate the beacon from the SMR. Earlier, I gave you an SMR black box from which we constructed the beacon. Here, they're very tightly coupled. So you use the randomness PVRS construction to optimistically move forward with the SMR. So they cannot be separated as easily. Yeah, the SMR needs the beacon to progress fast, and the beacon needs SMR for commitment and all these things. So they are kind of very tightly coupled. So okay, so let's look at what we did in the PVRS, right? So this is what generally a PVSS looks like. I'm not sure if the contrast is visible, but let me just tell you. The individual boxes are the encryptions, and the big boxes are commitments and a proof. So that was the G to the power P of 1, P of G to the power P of 2 that I described earlier. So that's all the commitments. And then there's a non-interactive zero-knowledge proof that says that the encryption 1 and the commitment 1 are having the same exponent. So these are all the proofs. Now, the problem with the existing scheme was we used a non-interactive zero-knowledge proof. That was the problem. Because of this, these are all the sizes, right? Each encryption is order 1 size. So it turns out all the encryptions are homomorphic. The commitments, G to the power P of 1 is homomorphic, right? I take 2 polynomials, I just multiply the corresponding ones. They all nicely become polynomials again. Very nice. But that non-interactive zero-knowledge proof was the problem. It wouldn't combine easily. It's not designed to be homomorphic. It just basically just blobs and aggregates, grows in size. If you combine 3, the size is 3x. So if you combine order t, the size is t times n, which is not good. So somehow we wanted magically homomorphic proofs that the encryption and the commitment have the same exponent. Turns out we had to go further in the original PVSS paper, right? So we were looking at section 1 in the scrape paper. That was the original paper that had PVSS. Section 2 solves our problem for us. So all we needed to do was read further. Turns out, yes, if you use section 2, you have proofs using pairings. So they construct a PVSS using pairings. Nice. Pairings means that there's no non-interactive zero-knowledge proof. You can combine everything homomorphically, still use the pairing property to confirm that they indeed have the same exponent. So, but just as is will not solve our problems, right? Now, because it's nicely homomorphic, there is another problem that pops up. Adversary can take t inputs, right? He can say, okay, let me take I still control one more input, right? So he can take t honest inputs and generate a secret share from one of these. Let's say it combines all of them, and he can generate a secret share for negative of that. So because it's g to the power p of 1, all he needs to do is raise it to the power minus 1. Everything becomes negative, right? G to the power minus p of 1, minus p of 2, minus p of n. And the proofs will still pass. Everything passes. But if you add this to the final randomness beacon, you cancelled out all the honest shares input to become something deterministic. And he can add some more additional polynomials to make it what he wants. So he has the power to bias this. This is not good, right? You don't want the adversary to negate or remove honest node shares. This is a problem we introduced with that scheme. We need to fix this. Turns out now you put zero knowledge proofs here and you will solve it. So how do you prevent an adversary from forging honest server's inputs? You say you have to prove that you know what's inside the exponent. And once you add this additional proof, so we call that as a decomposition proof. So each person, when they submit a PVSS to the leader, they're going to assign some zero knowledge proof saying, I know what's being secret shared. Here is a proof. This proof now an adversary cannot just combine and cancel out, because now he has to prove that he knows what's being cancelled. And if he knows it, he might as well break the secrecy. So he cannot do this. Because of this, turns out that, yeah, all he can do is either refuse to cooperate, like become a crash person, not input anything, or play correctly. This is the only two steps he can do. Yeah, we call this as decomposition proof. So one, it shows who it comes from. So there's a digital signature that says I sign it, so he can't fake it. Because of the digital signature, what is it signing? It's signing a zero knowledge proof. So there's no secret leakage of anything. And now what we're going to do is we send it to some dealer, right? This dealer is going to take combine all the PVSs and leave the individual decomposition proofs as is. And what you can do is check the decomposition proofs. Check they'll all commit. They'll all the zero decomposition proof argues that I know p of 0 or some element that this secret sharing corresponds to. So now you can just multiply all of them and check whether the PVRS also has the same zeroth polynomial evaluation. You can do this. This is just a math thing. Once you do that, you confirm that indeed it has inputs from all these people, or at least the product has inputs from all these people, and we achieved what we wanted. Now this PVRS is of size order n. From now on, you can do what Grand Pepper is doing, right? Post this one long string into the SMR, wait until t+1 rounds. Every time wait, see what they've previously committed, open it. Now you have a perfect randomness. So yeah, this is what we do. So everybody is going to start, pick some random numbers, and they're going to use PVRS scheme, right? So they're all going to feed this to some leader. Leader is going to combine them, build this decomposition proof-based PVRS, and input it to our SMR protocol. So our SMR protocol in t+1 rounds, again, without blowing up any communication complexity, outputs this sequence of PVRS values. And every round, they're going to open the last PVRS value that this person has committed. Again, we get the nice one absolute unpredictability property. Now the adaptive adversary has only 2 delta advantage. More importantly, I think the communication complexity is always n square. So we're kind of happy now. But we're still sad that you cannot prove secrecy is under an adaptive adversary. So we don't know, because we use PVSS, right? We don't know, these constructions are not proven to be adaptively secure. They are neither information theoretic, not UC provable. So we don't know how to prove adaptive secrecy as of May 2023, right? May 2023, Julian et al., they told us that they solved it. So they somehow were able to prove that this PVSS construction is adaptively secure. So which means that secrecy of this unpredictability requires secrecy of PVRS, and it has been proven to be adaptively secure. So thanks to them, we can now argue that his uptrend is also adaptively secure. So we solved that last leg, last missing leg. The assumptions that they use are algebraic group model, and asymmetric one more discrete log assumption. So under these assumptions, at least we are happy that we are adaptively secure. So future work, if you have spare cycles, you can think about how to construct asynchronous random beacons. It's tricky in asynchronous systems because asynchronous systems, to agree on things, it's not possible deterministically. So you need randomness to agree on things. If you need randomness to agree on things, like why are you doing a random beacon in the first place if you already had randomness? Or how are you going to generate this randomness without agreeing on things? So there is a chicken and egg problem here. So it's going to be interesting on how we'll solve this. Again, information theoretic random beacons are of independent interest to NIST, who wants post-quantum security, or even in general some random beacon that works. Because this is a service that keeps running forever, if you had an information theoretic system, that would be amazing, because it's going to outlast anything. Again, adaptively secure, optimal, efficient randomness beacons in general are open under may possibly reduced assumptions. So that will be the end of my talk, but I'm happy to receive questions.